All right. Hi, everyone. My name is Darius. I'm a PhD student at the National University of Singapore, and I'm very happy to present our work, automated temporal verification for algebraic effects. With my collaborator Yang Hui Song and my advisor Chu Wei An. So, this work is about specifying and verifying the temporal behaviors of programs which make use of algebraic effects, right? Which is a language feature that has made its way into many mainstream programming languages, including the upcoming OCaml 5. So what are algebraic effects? They are a mechanism for allowing users to extend a language with new computational effects, right? Things like not asynchronous I/O and non-determinism, which will otherwise have to be encoded in today's languages. So if you're familiar with monads in Haskell for managing state or promises for encoding asynchronous computations, effects serve a similar purpose, right? They are able to enrich programs with non-local control flow in a structured way. So this can be used to implement these new features. On the left, there is a program which recursively builds a tree of tasks using the operations fork and yield, which would typically be provided as primitives by some language runtime. So what algebraic effects allow us to do is to implement these two operations as a library. So you notice that f is wrapped in a function run, and within run is a so-called handler, which essentially provides an implementation for fork and yield. And this is completely decoupled from the program which uses fork and yield. So run could include something like a scheduler, which says, for example, the order in which tasks are resumed. And since the scheduler isn't built in, we can just replace it with another scheduler for testing, for example. Furthermore, fork and yield are usable in direct style, which is to say that we don't have to wrap any code in continuations, as we would with a bind operator. So they're quite natural to use and they feel like built-ins. So many language features, which are considered primitive operations in other languages today, like those in the list here, exceptions, generators, and so on, can all be implemented in this style. So I'll quickly walk through an example of how effects work. This program starts with the declaration of an effect named E. So we'll see what the type does later. Next, we have some effectful computation comp. So this prints 0, and then it prints the result of performing E, and then it prints 3. Right. So what does it mean to perform an effect? Operationally, effects are like resumable exceptions. So you can think of the perform as a throw, and there should be a handler somewhere else in the program which can catch it and resume and provide some value to resume the computation of comp with. So the type of this value, which is given at the resumption point, is what is given is declared together with the exception, the effect. And you can think of So in this example, the type is string, and it agrees with what is expected by print string, right, on the perform line. Next, we have the handler, which wraps comp. So it has one extra argument k, which is a continuation, and you can think of this as an evaluation context with a hole where the perform would be, right? And we can fill in the hole by providing a value and invoking continue. So the overall control flow of this whole program is when we start, we go into main, and then we execute comp and we print 0. Then we perform the effect, and this brings us to the handler where we print 1. And then we continue with the value 2, and we go back into comp, and then we print 3. And finally, because continue is, you can think of it as a function call, right? So when we return from comp, we are back in the handler, and then we print 4. Right? So that's the so we've seen that effects are very expressive in general. Right? We can implement new effects by just doing something interesting with the continuation. But the problem is that control flows resulting from the use of effects can be difficult to manage. For example, given some arbitrary function call in isolation without knowing anything about the implementation, we no longer know anything about the code after it, right, in the continuation, because the continuation could be run multiple times or not at all. So this leads quite naturally to these first two questions, right? Which can a given effect occur, and are all effects handled? So these are typically answered by type and effect systems today, right, which they decorate function types with like a multi-set of effects, so we can ensure that a function does what it's supposed to by just looking at its infer type. However, there are other questions you might want to ask. For example, if we had effects for performing file I/O, we should only be able to close a file that's already been opened, right? So effects, we might want to say that effects should be ordered in a certain way, and we only allow certain orders. And we would also like to specify and check this somehow. Finally, since we can pass arbitrary values between an effectful program and its handler, it's possible to pass another effectful program, right? So this may be handled by the same handler and lead to loops. So there is a snippet on the left, which is a very simplified version of the problem, right? So foo is an effect which, when performed, it produces a callback to be invoked, right? And so the perform in line 3 is actually a curry application, right? The perform foo performs the effect, and this returns a function from unit to unit, which is then applied to unit, right? And then we may perform further effects as the result of this program. So depending on what callback the handler passes, we may go into a loop where we repeatedly handle and perform the same effect, right? Because we are under the same handler at this point. So there's a more concrete example of this on the right. So for example, if we are implementing pagination in a database API, and we want to invert control and give the client the ability to choose when to get the next page, but we want to control the state of the next page. So the resumption should be based on the previous state, right? And an easy solution to this is to pass a closure, which tells the client what effect to perform next, right? So the point is that non-trivial flows can easily result from very natural-looking code, and we should provide some support for thinking about these things. So next, there's the problem of multi-shot continuations, which is when one is allowed to resume the same computation multiple times. There are many interesting use cases for this. For example, non-determinism or memoization or probabilistic programming. And multi-shot continuations are also well known to be incompatible with many things, mostly for the reason that, as on the right, we must now account for the fact that code that appears to run once may run multiple times, and this may break invariance. So there is an existing work which uses protocols to describe interactions between an effectful program and its handler. So this work uses separation logic, and we don't have the same scope, right? But because we don't handle heap reasoning in this work, however, we want to ensure that we have some provisions for treating multi-shot continuations right at the start. Finally, there's the challenge of modularity, which is key to the scalability of many verification approaches. So we want to be able to specify the behavior of effectful programs at function boundaries, right, so that we can think about them in isolation. However, we can only fully reason about what each function is doing in the context of its handler, which could be dynamically determined, right? And there could be many possible handlers, as in this example, where lots of different things could be printed depending on what the handler does, right? So the challenge here is to specify an effectful program in such a way that it can be verified under any handler. So this is a summary of the challenges we just covered and what our approach does to address them. So to have modularity, we implement our approach as a program logic with compositional temporal specifications, and we infer specifications for effectful programs, and then make use of only the specifications to verify handlers. We also make sure that it works in the most general setting with multi-shot continuations, and we have an additional fixed point analysis to check for some cases of non-termination due to deep handlers. So here's the high-level workflow of our approach. The user provides a program in an ML-like core language and annotates it with temporal specifications in a new language that we provide called ContEffs, which is based on regular expressions, and it allows users to specify allowed sets of traces. We then step forward through the program and infer a temporal specification for it. And then at this point, we also do some reasoning to check for potential non-termination. And the result of this stage is a set of proof obligations, right, which we can discharge using a combination of Z3 for pure formulae and a term rewriting system based on Brzezowski derivatives for deciding regular expression inclusion. So in the paper, we also prove soundness of the logic and termination of the term rewriting system. So I'll start by covering the core language really quickly and then show some examples of verified programs. So the core language we target is a very standard ML-like call by value lambda calculus. It has 3 effect-related primitives. So there are we can perform an effect, we can handle effects, and we can resume continuations. You might notice that perform is past the entire continuation as argument just for simplicity of presentation. Next is the temporal specification language. So at the top level, you can see that specifications are a disjunction of triples of a pure formula pi, a regular expression theta, and a return value v. So the regular expressions are quite standard extended with a few constructs. So they're either bottom, the empty trace, or a handled effect L, a wildcard representing any effect, or a negated effect representing any effect but this one. Right? So any effect but L. So having wildcards and negation allows for more modular specifications because we can ignore parts of traces that we don't care about. There's some examples of this later. Finally, there are placeholders Q. So the bang denotes an unhandled effect. And the question mark is a placeholder for any further effects which may arise from like a callback passed by a handler. So the rest of the operations are the usual sequencing and disjunction. We also have three kinds of repetition. It's finite, possibly infinite, and infinite repetition. So we reason about finite and infinite repetition together, and we just provide both for more precision in like writing specifications. So as a motivating example, here we have a few annotated functions for handling files. So on the left, we start by declaring two effects, open and close. So you'll notice that they have arrow types, right? The type on the left is a parameter type. So this is what the effectful program sends to the handler. And the handler then returns a value of type unit. Right? So that's what the syntax means. The first function we have is open file. So this takes an argument n, and its precondition is any star, right? Which indicates that any finite number of or kind of effects is allowed to have occurred before the call to open file. Right? So in other words, it is always possible to open a file. The post condition shows a summary of the function body's effects, which is just an unhandled open. So the complete trace actually should be any star dot open n, right? It should be the concatenation of these two, of the pre and post condition. But for brevity, we just show the post condition, and we just assume the precondition is always prepended. Close file has a more interesting precondition. So this can only be opened this can only be called after file n has been opened, right? But has not been closed, right? So we're able to constrain the allowed orderings here. And here you can see that the precondition is used to constrain the history, right? Or the context in which this function can be called. And separately, the body is summarized in the post condition, and they don't interact unless like there are constraints on n. Next, you have the precondition of file 9. So this is empty, which means the empty trace. So in effect, we can only call this function at the beginning of the program. Right? And the summary mirrors the body because the body consists only of effects. So since close file prevents closing a file twice, if we replace this function as follows, we will get like a precondition failure. However, because of the permissiveness of open file, we can leave files open or close them multiple times. Right? So that's just a flavor of how it works. Finally, the main post condition is very similar to the previous one. The difference is that the effects here are missing the bang, right, because they are handled. So now we've seen how some examples of this works. So I'll cover some examples now which shows the reasoning that happens at handlers. Right? So this is about effectful programs. So this first program is an example of a one-shot continuation, which is the usual case. So first, the two effects produce functions on resumption. Right? The x and y are actually functions because the types we declared at lines 1 and 2. Next, f performs two effects, and then it invokes the continuations returned. And from the post condition, you can see that there are two unhandled effects. But more importantly, there are placeholders, which stand for any effects which arise from the execution of closures which are passed back from the effect handler. Right, so these are effects that only the handler can tell us about. That's why we have placeholders in the effectful program. So this table shows the reasoning that takes place at handlers. So it's sort of like a symbolic execution of f against the handler. Right. So because f is called right at line 15, we check its precondition, which matches, so it's allowed to be called. And then we look up its postcondition, which is in step 1 of the table. Right, so this is the behavior we start with. And we split this into the current event and the current continuation. And then the next thing to do is check that there's a matching handler case for the current event foo. So we consider it handled, and then we move to the second step. And because the body is a continue, we can just continue moving forward, right? And at the same time, you might notice that we bind foo question mark and goo question mark to the functions that we encountered as arguments, as higher order arguments. So we just continue like this until we reach the placeholder goo, right, at line 3. So at this point, we look up the binding that we have and we infer the body of the effects of the body of the function. And because it's just unit, right, there's no effects. So we just append empty to the history at this point. So that's what gives us line 4. Right, and then we just do this for the full placeholder, and then the heart represents the end of the trace. Right, so at that point we just stop. And after some normalization, we get this final effect that we infer here. So the next one is an example of a zero-shot continuation where the continuation is abandoned. So in other words, this is like an exception that we just don't resume. F is pretty much the same except for different names. So we have the same starting point at line 1. So in the same way, we look for a matching handler and we consider EXC handle, right, at step 2. And then because the body is empty, we can end at that point. Right, so that's what gives us the final one. So this is an alternative termination condition. Next, we have a multi-shot example. So this is very similar. I'll just highlight the differences. The first is when we are done, when f has executed to completion, and there's nothing left to do, it returns a value which is bound to x, right? And at that point, we perform a done effect. So you can see that this, since it's performed in a branch of a handler, it's not actually handled by the handler, right? So it should be surfaced to the next level. And so we have an unhandled effect in the postcondition. And the next point is that there are two, it's a multi-shot resumption, right? So we resume the continuation twice, and that gives rise to the two goo dones that you see in the postcondition. So this operates in pretty much the same way, except you can see that now there's a copy of the entire trace after the initial event, right? And there are two end markers, which incidentally indicate where we can place the unhandled done effect, right? Because those are the points at which the trace ends and we return a value. Okay, so as a final example, here is the non-termination example from before. So here we are essentially looking for the reoccurrence of a sequence of effects during the symbolic execution. Right, so this time, the closure the handler passes has a postcondition, which we infer and we add to the trace. Right, so we can see that when we find the matching handler at line 15, we then bind the placeholder for foo to the argument of the continue. And when we infer the effects of this argument, we actually get the same thing back, right? Since this function is equivalent to f. So we append that to the current context, and then we find that we have actually seen it before, right? And then that's what gives us this full omega that we append to the history. And after some normalization, it's just full omega. So that's the final postcondition. So we don't actually raise a warning when this happens. We just infer something general to just communicate that this is what we have gotten from it. So this is we did some evaluation on top of some synthetic benchmarks. So we prototyped this on top of an old version of OCaml 5, back when it still had the syntax for all of this. So these benchmarks are all synthetic programs which we wrote specifications for by hand. And I guess the 2 points to note here are that the approach is relatively lightweight, right? Checking the inclusion of regular expressions it can be implemented quite efficiently. And also, the average disproving time is consistently lower than the average proving time, which agrees with the conventional wisdom that when using term rewriting, it's better average case performance, right? Because we can do it incrementally and we don't have to construct the entire automaton to disprove something. So to conclude and summarize what was presented, right, we showed a new specification language, which is based on regular expressions for specifying allowed traces of programs which use algebraic effects. And it distinguishes between handled and unhandled effects, supports multi-shot continuations, and can handle some cases of non-termination due to deep handlers. So this is used to modularly verify temporal properties of some small programs. And the evaluation shows that it scales quite well because of the modularity. And we are just handling each program in isolation, each function in isolation. So I would say the main challenge going forward is the expressiveness. So being able to adequately express enough in regular expressions to verify effect libraries, most of which use non-trivial heap state. So for that reason, the next step is probably to look at integrating some form of separation logic to handle heap reasoning. So that's all. Thank you.
Okay, questions? Shall I take the mic?
Yeah.
And you can speak into that one.
Thanks for that, Marcel. There's a sense in which worrying about resources for effect handlers is a bit of a red herring, because if you were writing like a highly concurrent code or a GUI code or a non-trick-oriented code, you would have to similarly worry about closing the same resources several times and so on. So what's new and specific about effect handlers that makes it more difficult, less difficult? What have you learned from effect handlers that can feed into those other applications or the other way around?
So I think what is new is the coexistence of like the flexibility, right? The coexistence of zero shot, single shot, and multi-shot continuations. Like because of like in general, I guess the same thing would apply with high order functions.
So I'm not sure if I understand this correctly. Are you basically verifying multi-core and camel code here, or is your object language that or something different?
Right. So it just uses the multi-core camel syntax for presentation, but it's a very small core language.
It's a core language. All right.
Yeah.
And it's also an extension because you support multi-shot, which camel doesn't.
Yes.
But you don't have an effect type system separate from the system you described here.
Yeah, there isn't. So it sort of functions as one in a very loose sense because it is very lightweight and simple.
Right. So the point I was just wanting to highlight is if you have an effect type system, then I think the kind of examples you gave where you've got non-termination are ruled out if you're using deep handlers. So it might be interesting to understand, well, what's the difference between your system and what an effect type system gives you then?
Right.
Or maybe how could you combine your analysis with an effect type system, and then you guarantee termination from the start?
Yeah, I think that would be an interesting question. The main, like we could look at that next. The main thing I guess which is different is that we can talk about the orderings of events, which is typically like I'm not sure how that would be, or at least it's not clear to me how it would be done in a typical like unification based set.
Hi, thank you. My question is, I wasn't sure how much is inferred and how much the user needs to input in terms of the notation. Can you clarify?
Right. So
like a big overhead to specify all that.
the part which is user provided is the part in comments. So just the top level pre and post condition.
Just stop it off.
if you leave it out, we will still infer something, but I think we use a very liberal post condition by default. So yeah, and essentially the verification just checks the inferred effect specification against the provided one. So that's what the difference is.
Other questions? So I have one. First of all, this is really cool. I was just teaching continuations and algebraic effects in my class the other day, and following the details of the control flow really is mind bending. So it would be great to have some guidance here. I'm curious, what kind of error messages are you able to give? I worry a little bit that they could be complex, but I also wonder if your structure and your modularity might help with that.
Yeah, so currently, I think the error messages probably wouldn't be great if you actually tried to run it now. But I think the modularity would help with that, because we can tell pretty much. So what we could produce is the intermediate state of the inclusion disproof, where we could say that, oh, at this point, this is where it fails. So I think that is something you could do.
Yeah. Cool.
So one use of more nuanced effect, because in this case resource tracking, is kind of some sort of selective compilation. You allocate things earlier and so on. Have you thought about using your analysis for doing some more efficient preparation?
That's not. I don't think we've done that. But what sorts of how are effects used?
In Coq, I was compiling the same piece of code in different ways depending on how you instantiate the effects, and that leads to some speed ups in some cases, for example. But that's only for the effects, right? If you're doing resources, maybe you can do something a little bit different in terms of managing where things maybe allocated earlier or something like that.
Yeah, I'll probably have to talk to you later about this.
Results, sorry.
All right, maybe one last question, a little bit forward-looking perhaps, but I was thinking as you were talking that because algebraic effects are modular and they return, that it would be natural to think of not just regular expressions, but context-free grammars. Did you think about that at all? Is that potential future work? Or is that potentially undecidable? I don't know.
Definitely an interesting question. We've not thought about it.
Yeah. Okay. Well, it's a great first step, and looks like there's lots of directions to go. Thank you very much.